Okay, hello everyone. So in this video, we're asked to prove that any DFA that accepts the following language L must have at least 6 states, where the language L is a language that we already saw and already created a DFA for. And it's the set of all strings over the alphabet 0, 1, such that the string starts with 0, 1 and ends with 1, 0. Okay. And so our task in this exercise isn't to build a DFA that accepts this language, and it's not to prove the correctness of the DFA that accepts this language, but rather it's to prove that for any DFA that you were to build, okay, it would have to have at least 6 states, okay? And so to do this, I'm going to present a general proof technique for solving this kind of question. And some of the ideas contained in this proof technique, some of the intuitions that come out of it, are also used to, for instance, prove the correctness of the state reduction algorithm, which takes any DFA and then converts it to an equivalent minimal DFA. Okay? If you don't know what a minimal DFA is, I suggest checking out the other videos on minimal DFAs. But in this video, we're going to actually focus on this particular language and this particular question. Okay, so what's the general idea? So first of all, what's the general goal? The goal really of what you want to do. And when I talk about the language L here, I'm going to be in particular referencing this L. Okay, so what I want to do here is I want to show that any DFA M such that the language accepted by M is equal to L, right? So L is this particular L here, will have at least 6 states. Okay, this is what I want to show. So any machine that I build, so maybe I have M1, M2, M3, and so on, each of these has a set of states, okay? And so I need to show that the cardinality of each of these sets will be at least 6, okay? And so how do I actually do that? So the proof technique is going to be the following, okay? So I'm going to consider, okay, I'm going to consider any DFA, okay, consider any DFA M with 6 states, such that the language accepted by M is equal to L. So I say, consider an arbitrary machine, M, it's a DFA, and it has 6 states. Then what I do is I denote the 6 states. So I give them labels, but I don't specify a particular architecture. Okay, so I denote the 6 states of some arbitrary, well, I guess it's of this arbitrary, okay, arbitrary. So for instance, I could label them S1, S2, and so on until S6. Okay. The next thing that I do, okay, is, so this is step 1, this is step 2, then step 3 is I pick 6 particular strings. So now I choose 6 particular strings, okay. So let's denote these strings W1, W1, W2, W3, W6, okay? That I assume, okay, so I choose 6 particular strings, W1 to W6, that are assumed to go to one of the 6 states, S1 to S6. And so out of convenience, so for convenience, right, I'll suppose that from Q0 reading, or I shouldn't have specified a Q0, right? So forget about a particular Q0. Let's just suppose that W1 read by M ends at S1. So from the start state, some start state of my machine to S1, I can go along the walk W1, okay? So essentially what I'm saying is I'm saying from my start state in M, I can reach S1 with W1. And then I do the same thing for W2. I assume this for S2, and so on until W6. Okay? And so I haven't assumed anything. Okay? So the key here, the key of this technique, right? The key is never assume anything about the transitions of M, about the transition function of M. Okay? So the only thing I'm assuming, right, is I'm assuming that I pick some machine M with 6 states that accepts the language L. Okay? So I name these 6 states, right? It doesn't really matter what I call them. It could be A, B, C. In this case, I just number them S1, S2 to S6, right? Okay. And I say each of these states has a string that goes to it, right? It has to have a string that goes to it. Otherwise, that state would be useless, and I wouldn't have picked a DFA with 6 states. Actually, the DFA would have had 5 useful states. Okay, so I have these 6 arbitrary states, right, which are each reachable, and I have these 6 strings that go to each of these states. So really, in other words, I'm just mapping, I'm just picking, so these 2 steps go together, okay? And the more important thing is actually how you choose the 6 particular states, and I'll get into that in a second, okay? But really, the important thing is to note that I have these 6 strings, and each of them goes to a state, okay? Okay, and then comes the crux of proof, right? Is that what I do is for every possible pair of states, Si, Sj, right? I assume for the sake of deriving a contradiction, that these 2 states are in fact the same, okay? That these 2 states are in fact the same, okay? And so what I'm trying to say is, I want to prove that any machine that accepts L has to have at least 6 states. So now I'm saying, okay, well, pick one of the machines that does have 6 states, right? Pick some arbitrary machine that does have 6 states, and show that it's actually impossible to to reduce the number of states further. And how do you reduce the number of states further? You can collapse states together, right? So by collapsing, this is what I mean by saying Si equal to Sj. So imagine in my machine I have Si and then Sj. To reduce the number of states in my machine, what I could do is I could just collapse these two states together, okay? Getting a machine with a smaller number of states, okay? Okay, so I assume, for the sake of deriving contradiction, that these two states are the same. Now, I derive a contradiction based on the fact that Wi goes to Si and Wj goes to Sj. So based on these two facts and the nature of the language L. Okay, and so you'll notice that in none of the steps I've listed here, okay, and this is very important, right? This is very, very important. None of the steps 1 to 4 assume a particular transition function for m, right? For m. And in fact, the only place that we're actually going to use a particular DFA is in step 3 when we actually choose the strings, the 6 strings, okay? And so that's the only extra thing that you need to know. So how do you choose? Do you choose W1 to W6? You can use a DFA with 6 states that accepts L. Okay, and that's what we're going to do. Now that I've sort of given you the proof technique, the general idea, we're going to look at a quick example. Okay, well, we're not going to look at the quick example, we're going to actually solve the question, right? So from a previous video, we've already created a DFA that accepts L. So this is a particular, right? So this is a particular M prime such that the language accepted by M prime is L, okay? And here L, I specifically mean the strings that start with 0, 1 and end with 1, 0. Okay, so this is the particular L I'm referring to, and this is the particular machine I'm referring to. So this is my machine M prime. Okay, and now let's suppose I've assumed some arbitrary machine M, right? So I assume M is some machine, which is a DFA, with 6 states, such that L of M is equal to L. So what M prime tells us is that there does exist at least one machine with 6 states that accepts L, right? So M prime tells us that this assumption, okay, is a harmless assumption, right? That I'm not breaking any rules by making this assumption, right? So this is possible because M prime proves the existence of one such machine. Okay, so I guess here I can say that I'm actually starting the proof to the question. Okay, so M is some machine with 6 states. I label these 6 states S1, S2, S3, S4, S5, S6. And now it's the time to pick the 6 strings. And to pick the 6 strings, I'll use how the machine M prime works, okay? And the game I'm going to play is I'm going to try to pick strings that go to different states in the machine M prime, okay? So, for instance, I know that the string, I know that the string 1 goes to Q1, right? I know that the string 0 goes to Q2. I know that 0, 1 goes to Q3. I know that 0, 1, 0 goes to Q4. Right, so yeah. Whoops. 0, 1, 0 goes to Q4. 0, 1, 0, 0 goes to Q5. 0, 1, 0, 0 goes to Q5. So I have 1, 2, 3, 4, 5. So I'm missing a string, right? And that's the string that should go to Q0. Okay. Well, the only string that actually goes to Q0 is the empty string. Okay. So I've picked 6 strings, right? It doesn't matter in which order I assigned them to S1 to X6, to S1 to X6. God, I'm confusing my French and my English. So let's just say that S1 is, you know what, let's just go in arbitrary order. So S1 could be, say, 0, 1, S2. So what I mean here, just to be clear, what I mean is this is the string going to SI. To SI. Okay? So 0, 1 for S1. Let's pick 0 for S2. 0, 1 for S3. 0, 1, 0 for S4. 0, 1, 0, 0 for S5. And then the empty string for S6. Okay? Okay. And so now what I need to do, right, I need to assume for each pair, right? So for each pair, how many pairs do I have? Well, if you'll recall from your combinatorics class, I have 6 elements here, and I'm choosing 2 elements, right? So I have 6 choose 2 pairs. I actually didn't think about doing this mental calculation in my head, so I don't really remember. I can't do it off the top of my head what 6 choose 2 is. So it's 2 factorial, 4 factorial. So this cancels with 6 times 5, 2, and then this cancels with 3, 15. Okay, so there's 15 pairs. I didn't think there'd be that many, but yeah, okay. So there's 6 choose 2, or 15 pairs of strings. Okay, so now what I need to do is I need to assume for each of these 15 pairs that the states are the same and then derive a contradiction. So, okay, having not realized how long this would be, I'm not going to do all 15. I'm going to show you a few, and you should probably be able to do the rest yourself. So, let's assume for the purposes, right, so this is the acronym I use for the purposes of deriving a contradiction, that let's say S1 is equal to S2. Okay. Well, what that means that in my arbitrary machine M, I have the state S1 and I have the state S2. And now these two states have been merged together. Okay. What that means is that the string W1, okay, which is equal to 0, 1, and the string W2, which is equal to 0, both of these strings go to the same state, right? So W1 and W2 go to the same state. Okay? So now what I need to do, okay, is I need to derive a contradiction based on the nature of the language L. So how do I actually do that? Well, remember what the actual machine M is supposed to accept. So, um, so let's say this is 1 of 15 here. Okay. Recall M accepts strings that start with 0, 1 and end with 1, 0. So for instance, M should accept, or actually it's not that it should, it's that it does. M accepts 0, 1, 0, right? Because this string starts with 0, 1 and it ends with 1, 0. And this is what we have to take advantage of. It's actually this particular counterexample that's going to lead us to a contradiction. Because this is my arbitrary machine M, right? The only thing that I know is that now, because of my assumption, 0, 1 and 0 both end in the same state, okay? So now if I append any string to W1 and W2, okay, both of these newly concatenated strings should end in the same state, right? Because if 0, 1, right, so if 0, 1 and 0 end in the same state, that means that 0, 1 goes to this state and 0 does the same. So now if you concatenate any string to these two strings, let's say you concatenate the string V, then 0, 1 V and 0 V will end up in the same state, right? Okay, but now suppose based on this observation here, based on the above observation, suppose that we stick 0 to both 0, 1 and 0, right? So we have this new string v1, which is w1 concatenate 0, and this new string v2, which is w2 concatenate 0, right? So v1 is 0, 1, 0, and v2 is 0, 0. So what this means, right? This means v2, wait, sorry, not v2, v2 and v1, or v1 and v2 end in the same state in M, okay? But, and this is where the contradiction happens, but v1 belongs to L and v2 does not. So what that means is that because of v1, because of what v1 is, it's 0, 1, 0, and because of the nature of L, v1 should end up in a final state, but because of the nature of v2, which is 0, 0, and the nature of L, V2 should not end up in a final state. And so we have a contradiction, right? Because that means that if I were to collapse these two states together, right, then I have two strings, right, which should end up in the final state. I have two strings which should end in the same state, where for one of these strings, this state should be a final state, and where for this other string, this state should not be a final state. So that's a contradiction. And so we have a contradiction. Okay? And we can repeat the same thing. So we can do another pair, let's say 0, 1, 0, 0, and lambda, right? So we can repeat this. So this is 2 of 15. So suppose S5 was equal to S6, right? So now I'm collapsing two other arbitrary states of this arbitrary machine. Well, they're arbitrary up to the fact that these two strings go to them, right? So then I have that 0, 1, 0, 0, that goes to the same state as lambda, right? But now if I append a 1, right? If I append a 1, then this string will start with 0, 1 and will end with 0, 1. That's not what I need yet. Actually, I need to append 1, 0, right? So, because then I'll have a string, so I'll have this string appended with this string, which will create 0, 1, 0, 0, 1, 0. So this is in L. And so in the DFA, this should lead to an accept state, right? In this collapsed DFA. However, lambda concatenated with 1, 0, right? Lambda concatenated with 1, 0, that'll be 1, 0. And this is not in L, right? And so 1, 0 should end up in a non-accept state. And so again, we have a contradiction. So again, contradiction. And you can do this for each of the 15 pairs of states. Of course, you can find some quick tricks to kind of reduce the search space, because you know that, let's say, you know that 0, 1, 0, this is in L, and so it's accepted by the machine M. So if you pair this with any of the other strings, which are not in L and therefore are not accepted by M, then if you concatenate each of those strings, like if you concatenate each of the pair of strings with lambda, then you're going to get contradictions, because 0, 1, 0 lambda is 0, 1, 0. That's an L, so that should be in a final state. But any of the other strings, say 0, 1, concat lambda, that's still 0, 1. That's not an L, and so that should not end up in a final state, right? So right there, I eliminated 5 cases, or 5 pairs very quickly, okay? But so this is the general idea of how you can prove that this particular machine, well, not this particular machine, but that any machine, right, that any DFA that accepts this language, this particular language, must have at least 6 states, okay? And that's how you could do it for any language L. So if you had replaced this language L by something else, and you had replaced the number of states by some other number, then you would use the same kind of procedure to prove this, okay? And so the only thing that you can't do, right, so beware, what you can't do, you can't start with a particular machine M and argue that its particular states, right, that its particular states can be collapsed. So what I'm saying here is I'm saying You can't say, well, take this machine, and now suppose I took this and I collapse it with this, then I get a contradiction. You can't do that because you're not applying this argument on an arbitrary machine M with 6 states. Okay. The other way you